Thank you very much, Greg. It's a pleasure to be here. So the title, as advertised, is Ultra Spooky Action at a Distance, from quantum materials in the lab to black holes. So I'm going to start out by just explaining everything in the title. In particular, what is this spooky action at a distance that's playing now a fundamental role in many fields of physics. My own research is on, as Greg mentioned, what we sometimes call ultra quantum matter, and I'll give you some examples of that today. But surprisingly, the things that have come up in studying ultra quantum matter have also led to new insights and new pictures of what happens to the quantum theory near black holes. And I'll try to give you some flavor of that connection that's occupying many of us in this field today. All right, so I showed you all there was this teaser slide of an article from the New York Times showing experimental evidence for this strange, spooky action at a distance feature of quantum mechanics. So quantum mechanics is the theory of our universe at the microscopic scale. But when you extrapolate it to larger distances, it seems to predict some rather bizarre things. In particular, it appears to predict that when you measure a particle here, it can instantaneously influence the state of a different particle, which in principle could be really far away. So this was one such experiment looking at this kind of spooky action at a distance over a few kilometers, which was highlighted in the New York Times about 5 years ago. All right, but let me start at the very beginning and just introduce the central idea that's going to play a role in my presentation, which is quantum entanglement, so which is another key central feature of quantum mechanics. Before we get there, however, let me review the first central feature of quantum mechanics, which is already clear in this famous experiment called the double slit experiment. So imagine you have two slits here through which you're sending in, for example, water waves. And a characteristic feature of waves is that they cause an interference that you can see here. You have these regions of dark and regions of oscillations. And if you look at what's happening on the screen, you can detect, you see these oscillations, and that's a telltale signature that what you're detecting are waves that are hitting the screen. Now imagine doing that experiment with electrons. These are the electrons you might find in the old TV tubes, and send these electrons through two slits. The famous double slit experiment shows quite remarkably that with electrons too, you see this variation in intensity on this side, which is characteristic of waves. So, all right, so that seems like a reasonable claim. So we just conclude the electron's a wave, and just like water. But it's really much more subtle than that. And the subtle point is that, as you can see from the simulation, the electrons arrive one by one. So if I looked at just one electron and I saw one blip on the screen, it would be in some specific place. And it's only when I take thousands of such electrons and average over many, many, many such measurements, is the average of all those measurements gives me an observation that looks like a wave. So it really it has both. This is the famous wave-particle duality. The electrons arrive one by one like particles, but nevertheless, where they end up is very much like waves. And this is what we have to get our head around. So, of course, people have proposed a solution which not only explains this experiment, but many millions of other experiments. So everyone believes the solution is correct. And that solution involves introducing a whole new concept in physics that didn't exist, say, in the Newtonian view of physics. In the Newtonian view of physics, every particle is at a definite place at a given time and has some velocity. And once you know this information, you can predict the future of the world. But here we have to imagine something more subtle, and that's the idea of superposition. So we have here's the same picture here. You have this electron gun sending a bunch of electrons through. And it seems like some of them go through the left and some of them go through the right, which is natural for a particle. But nevertheless, when you look at what happens on the screen, you see this wave-like interference. So the way we encapsulate this, and this is the main idea that quantum mechanics introduced, is first of all the idea of a state. that let's just imagine that the electron going through the left slit is in a certain state I'll call L, and an electron going through the right slit is a certain state that I'll call R. And what we want to do now is imagine that we can add these states together. This is something you could never do in the Newtonian world. There's no sense in which an electron here and an electron there can be added to each other. It doesn't mean anything. Here, but we imagine we have this space called the states, set of states of an electron, and that space has this feature that you can add and subtract them. Okay, so that's what you have to accept is how the way our universe works. So starting with this idea, you can, of course, work through many other calculations of what happens to an electron in a hydrogen atom. It can also describe formation of molecules. It can describe the entire periodic table. So this very simple idea of superposition had enormous consequences. And there's no doubt it's correct. There's never been any observation that's contradicted this particular idea. So this is really what you have to accept. And now let's explore the consequences of what are the strange things superposition implies. So let's take the idea of superposition now and apply it to more than one particle. So that was just one electron, could be either left or right, or the sum of them. Let's take two electrons. So here's one electron in a hydrogen atom. Now one other feature I'll need about the electron that has a spin. And without explaining any detail, let's just imagine that the electron can only spin in one of two directions, clockwise or anti-clockwise. So it's spinning on its axis. And this up is one of the directions. So when I say this electron spin up, let's say it's spinning clockwise. All right, so now I take not a single electron, but I take two of them, as you find in a hydrogen molecule. And a very simple description of what the electrons do in a hydrogen molecule is they form this superposition or entangled state. So there's one state in which the left electron is up and the right electron is down. And maybe in a given molecule, that's where the electrons are at a given instant. But if you, in the stationary state, if we just take a hydrogen molecule out in space, that's not the way the electrons are situated. They're in a superposition state, where it's a superposition of up-down, but also the other possibility where the left one is down and the other is up. And it's really in both. Just like the electron going through the slit was both left and right, this pair of electrons is correlated. So if one is up, the other is down. But more precisely speaking, it's really entangled. And it's really in both states at any given time. And we represent this by this particular superposition. Don't worry about the minus sign. OK, so why is that a plus or a minus? Well, that's something we're going to have to leave for your first quantum mechanics class. OK. All right, so that's what happens in a hydrogen molecule. And this is really the basis of what we call covalent bonding. This particular entanglement or superposition of two electrons is the basis of covalent bonds, which is the basis of organic chemistry, which eventually leads to life. So it's really very much there on the microscopic scale in many, many molecules. All right. So, however, Einstein in particular, along with Podolsky and Rosen, pointed out that this led to some conceptual difficulties that he was very unhappy with. So imagine I take this hydrogen molecule, and now I separate the electrons without disturbing their spin. Now, in practice, that's extremely hard to do because any magnetic field will disturb the spin. So no one's really done this type of experiment, as far as I know. But you can do it with light. So light also is made up of little quanta called photons. And photons can spin one way or the other. And the experiment I showed you at the very beginning did exactly that. It took two quanta of photons and separated them. So now, but let's imagine that we could do that with electrons. It was just a little simpler to consider. So we take this, these two electrons, and I put one here and one, say, in Boston. So what would quantum mechanics say? The quantum mechanics would say, it's not yet determined whether the electron I have here is up or down. What I know for sure is that if I look at this electron here, and I happen to see it's up, then at that very instance, the electron in Boston is down. or vice versa. If I happen to see down, it's up. But before I looked at it, before I disturbed the system, it was in an entangled state where both were up and down. Now you might say, well, this is all one of those philosophical absurdities. Who cares about what it was when you didn't look at it? How do you know? So maybe you're just wrong, and it was one way, and you really don't understand what's going on with electrons. It's got other features that you don't know about. So people have certainly asked that question, and these are sometimes called hidden variable theories. And so there's a more subtle set of measurements you have to do to eliminate that philosophical question of, you're making statements about things that you didn't look at, so, well, maybe you're wrong. So you have to do multiple measurements, and then in the end, the only conclusion from those measurements, and using something called Bell's inequality, is indeed it's true that before you looked at it, this electron was neither up nor down. It's only after you looked at it that you determine the state of the other. All right, so this is sometimes called a paradox, because Einstein didn't, it seems as if this electron is determining what's happening very far away, something Einstein found quite unpalatable. But it's really not a paradox. It's not any pair of electrons that will do this. It's only electrons that have interacted in the past. And what you have to allow for this concept to make sense and not violate any sense of causality or signals traveling faster than the speed of light, is that the idea of a quantum state is not a local one. The state of these two electrons is neither here nor in Boston. It's nowhere. It's just a state that they shared, and they got entangled with each other sometime in the past when they were both here. And then you separated them, and they just have memory of that state. It's not living here nor there. Okay, so once you accept that what you mean by a quantum system is not a local concept, all of this, everything else really does not lead to any paradoxes. Okay, all right, so that's end of quantum 102. So now you know both what's quantum superposition and quantum entanglement. So now let's apply it in more exotic or ultra situations. So one situation I want to consider first is black holes. So let me just introduce what a black hole is. A black hole is something that was originally predicted by Einstein's theory of general relativity. It's a very dense region of space. In particular, if you take any mass m and you squeeze it down to a radius smaller than this radius r, where g is Newton's constant and c is the velocity of light, then you get a black hole. And what happens in a black hole is that there's no possible way, at least in Newtonian and Einstein mechanics, for any signal to go outside the black hole from the inside. So if you were living inside here and you sent a beam of light, it would just turn around and come back because of the intense gravitation pull of the black hole. It's so intense that light itself cannot escape. So we say that inside there is a horizon, and physics inside the horizon is causally disconnected, cannot influence anything that happens outside. You can certainly throw things from outside to inside and then change the mass of the black hole, but you'd never know what's going on inside because nobody inside could send any signal out. All right, so that was one of the predictions of Einstein's theory. At that time, there were no black holes known. Today, there's, I don't know, maybe thousands or millions of them known, and every galaxy at its center has a supermassive black hole, including our own, and astronomers studying them quite routinely. So now let me turn to the following question. What about quantum mechanics near a black hole? So classically, we know that nothing can ever go out of a black hole, but can something strange happen quantum mechanically? So this is something that Bekenstein and Hawking considered in the 70s. And one simple way to present what they talked about, let's take our simple experiment here of a pair of entangled electrons and separate them by throwing one inside a black hole and keeping one outside. I mean, imagine you could do such a thing and do it without disturbing their spin. Well, then quantum mechanics said that they're still entangled. So it is true that if somebody measures this particle, well, let's say that's inside, somebody measures this particle inside the black hole horizon, that will determine the state of the particle outside. So they're still entangled, and so something happening here can influence what happens outside, although classically that was impossible. So this is really the only logical conclusion from applying quantum mechanics to a black hole horizon. You can entangle, entanglement knows no barrier, including the horizon of a black hole. Okay, so in fact, so if this is down, that's up, and if the other one is up, the other one is down. Okay. So there's quantum entanglement between the inside and outside of a black hole. And Bekenstein and Hawking showed that this led to some observable consequences. And one of the conclusions of Hawking, this is one of his most famous results, that every black hole has an entropy, meaning it's like some hot body which is random, like a hot cup of water. So it has a temperature and an associated entropy. And what's the origin of this? Well, the origin of this is also this sort of entanglement. Because imagine I'm outside here, outside the black hole. It's true that somebody measuring this inside will influence what happens outside, but I have no way of contacting them. There's no information that they can send me because they just know it, tell me what's going on inside. So as far as I'm concerned, my little electron here is just completely random. Because in my view of the universe, this is either randomly 50% up and 50% down, and is not correlated anywhere with the part of the universe that I can communicate with. So therefore, it's as if there's a temperature. It's got some entropy and a temperature. So Hawking, in fact, gave a formula for this temperature, which I'll just call the Hawking temperature in terms of the mass of the black hole, and this quantum variable called Planck's constant. And one other thing that Bekenstein and Hawking noted was that the entropy is proportional to the surface area. And you can see that from this simple picture here. If you think of entropy as entanglement across the surface of the black hole, it's only the surface part that matters. So it makes sense that the entropy is just proportional to the surface area. But this is also quite a remarkable conclusion, because nothing else we know in the lab has this property. If you take a cup of water and heat it up, well, you're heating all of the water, and the entropy is proportional to the volume, not the surface area. So every physical system, except under intense gravity other than a black hole, has the property that its entropy is proportional to its volume, not to its surface area. All right. So that's another important property of black holes that I'm going to need. Okay. All right, so now I want to introduce one more property. Let me introduce in the context of this famous experiment done by LIGO on the merger of two black holes. This was, I guess, also about 5 years ago. So here's the kind of signal that the LIGO observed. Well, let's think of it in terms of these pictures. Here are two black holes which are spinning and eventually merge. And once they merge, they become this perfect sphere, which has a certain temperature. So we can think of the merged black hole as a body in thermal equilibrium. So you can ask then, well, how long does this body takes to come to rest? So that's what's called the ring down time. That's the very last tiny piece of this oscillation here. They don't quite have the resolution for this black hole to see the ring down. But that's something you can compute. How long does it take for this black hole to come to rest? And it's this formula here. For this particular black hole, it's about 8 milliseconds. Now, it turns out, if you compare this ring down time to the Hawking temperature, there's a very simple expression for it. And this is the main equation that I'm going to need for the rest of my talk. The ring down time of a black hole is given by this very simple formula. H bar is what's called Planck's constant. It's a fundamental constant of quantum mechanics. Kb is just a fake constant because we refuse to measure temperature in units of energy, but silly things like degrees Kelvin or Fahrenheit. So if you just measure temperature and energy, you don't need Kb. So it's really H bar over T. Forget the Kb. So you just take a universal constant of nature that controls all of quantum mechanics, H bar, and divide it by the Hawking temperature. You get a time, it turns out. And that time is basically a universal property of all black holes. And it's a bit mysterious. I mean, if you solve many different variations of gravity, different types of black holes, you always find this is the natural time. And I don't think it was properly understood until developments in the last 15 years, why it's so universal. Anyway, so to put everything together, these are the three things about black holes that I would like you to remember. They have a temperature, they have an entropy proportional to the surface area, and they have a ring down time, no problem, sometimes called the Planckian time, because it's just determined by Planck's constant and the Hawking temperature, and it's kind of a universal feature of many black holes. And why it's this value is something I'll say a bit more about, but it's really one of the fundamental consequences of the strange sort of entanglement you have across a black hole horizon. All right, so that's all we need to know about black holes, those three facts. Now let me turn to something entirely different. So I'm going to talk about ordinary materials in the lab, some of which are ordinary quantum materials, and some of which are strange or ultra quantum, and also some of them are metals and others are superconductors. So ordinary metals, here's like silver or gold, are very good conductors of electricity. And why is that? Well, it turns out that in these materials, the electrons, which normally are bound to their respective atoms, get delocalized. They just get liberated from the atoms and they run through the entire crystal. And as they're moving around, they're able to carry current, which is, of course, of very great use to us in many electronic devices. So now as these electrons are moving around, they bump into each other. In fact, they repel each other by the Coulomb interaction. And so you might wonder, how much does the fact that the electrons are bumping into each other influence the way current flows? And in ordinary metals, it turns out not too much. All you have to do is instead of thinking of a single electron moving, you think of an electron with a cloud of its neighbors. And that whole composite object you call a quasi-electron or a quasi-particle. And after you put the word quasi in front of everything, you pretty much get a pretty good theory of what happens in a metal. And that's the summary of solid-state physics 1 and 2 that you would learn in graduate school. And that's really all you need to know, that things get a little quasi, but other than that, it's as if the particles are moving around independent of each other. So one of the consequences of this quasi-particle theory is you can compute the resistance. You have a bunch of little wire, you want to compute what's the resistance of this wire. And you can relate the resistance of the wire to some basic quantities. Okay, I lied, there's another formula I'm going to introduce called the Judo formula, which converts the resistance that you measure to a time. So what the Judo formula tells you, that if you know the density of electrons n, the charge on an electron e, and the mass of this quasi-object, m star, then you plug it into this formula and you get a time, and this time tau is the scattering time. So that these electrons, even after they become quasi, these floppy objects will eventually collide with each other. They're not totally independent of each other. So those collisions are very rare, and tau is the time between collisions. And as you cool a metal, it becomes a better and better conductor because this time becomes longer and longer. In fact, it diverges as 1 over temperature squared. That's one of the fundamental consequences of quantum mechanics of electrons in a metal. So as temperature goes to 0, this time becomes much longer than this Planckian time, which will also play a role in the materials I'm going to show you in a minute. All right. However, so that's enough of the ordinary metals. Now let's talk about an example of what we're now calling ultra-quantum matter. So here's an example of ultra-quantum matter. It's this crystal of yttrium, barium, copper oxide. Here's an actual piece of it. It's made up of a combination of these elements, so that looks like quite a mess. But it turns out that all you need to pay attention to are these copper atoms, which actually sit on the vertices of a square lattice, these orange circles here, and you just ignore all the other layers. So basically, the electrons are moving in these layers and hopping from copper atom to copper atom. So this material, so here's a picture of the copper atoms and the electrons on each of them. And if you're at an electron density, if there's exactly 1 electron for each copper atom, they form this particular arrangement called an antiferromagnet, sort of like the squares of a chessboard, where the black squares have the electron pointing one way, and the other squares have the electron pointing the other way. And you can actually see this particular arrangement in various experiments. Now, this particular arrangement of electrons doesn't have entanglement. They're just correlated with up and down, but they're not in the superposition state that I told you about in a hydrogen molecule yet. So now what you have to do to get something interesting to happen is you change the density. You remove a few of the electrons. And this you do by varying the oxygen content of the crystal. And now you find that these electrons can move around. So here's one electron moving, and there's another one moving. And now you see there's something funny happened here. These two electrons are pointing the same way, and these are also pointing the same way. So they don't like to do that, so these two electrons will then flip, and now everyone's happy, and so on. So this is my job, figure out and write down equations on what these electrons are doing on the square lattice. This is a problem that I've been working on for over 2 decades. Simple enough, but it leads to incredible physics. So what happens? Well, really, us theorists fail in describing what happens here. We have to turn to experiments. So in experiments, you get this picture shown here, where the vertical axis is temperature, and the horizontal axis, the density of these electrons. This is the case where you had exactly one electron on each side. That's the antiferromagnet, that's the AF. And when you increase the density, lo and behold, this is why we're so excited, you get what's called a superconductor. And in particular, the superconductor is present even at temperatures as high as 100 Kelvin. Now, 100 Kelvin that's minus 173 degrees Celsius. And don't ask me what it is in Fahrenheit. So it's very cold, but it's not that cold. It's warmer than liquid nitrogen. So I'm sure you've all seen a little flask of liquid nitrogen. So if you throw something in there, that goes to about 70 Kelvin. So if you take this crystal of YbCO, you throw it in liquid nitrogen, you get a superconductor. And this was really the very first material that you could do that to. Superconductivity was discovered in 1911, but at much, much lower temperature, where you need a fridge the size of a laboratory to do the experiment. But now you can just do it in ordinary liquid nitrogen, a very common liquid. So here's one of the remarkable things you can find. So here's a little cake of YbCO, which has been dipped in liquid nitrogen. And this is a track of magnets. And if you give it a push, well, it floats around there. All right, so now it crashed. I'm sure you can all guess why it crashed. It warmed up, exactly. So by this time, it's gone above 100 Kelvin. So it's no longer superconducting, and therefore it doesn't float anymore longer. So the essential property of superconductivity is the ability of electrons to flow without any resistance, and that also gives them an ability to repel or remove the magnetic field inside the object. So as a consequence, this cake of YbCO wants to float above the magnetic field because it can expel all of it inside, and it can do that easier when it's a little bit away from the track. Now, superconductors are used in many devices around us, and maybe more in the future. This is a slide given to me by my colleague Seamus Davis. So in particular, they're used in MRI machines to create intense magnetic fields. They're used in particle accelerators, like the one in Geneva. Maybe they're going to be used, they're used a little bit now for high density power transmission in big cities, perhaps maglev trains and so on. So this is one of the reasons we're interested in superconductivity, because there are many potential applications in the future, although I shouldn't minimize many of the technological hurdles. But that's not why I'm interested in this. Well, it's good that people are excited about superconductivity. But one of the most interesting features of these materials is not the superconductivity itself, it's this strange metal up here. So when you heat it up, you'd expect, okay, now you're at some reasonable room temperature or so, maybe it should behave like a piece of copper. But it doesn't at all, and that's really what we've been trying to study and understand. And the essence of what's going on here is very much related to quantum entanglement, where the basic idea of these quasi-electrons moving around independently from each other fails completely. In particular, if you use this formula I showed you earlier between the resistivity and a time, Now, this is derived using the quasi-particle picture, but if we just go ahead and say, let me use it anyway for the strange metal and deduce what the value of tau is, you find, surprise, surprise, it's the same time that I mentioned earlier for a black hole. It's the time that you can create out of temperature and Planck's constant. It's almost exactly that. And furthermore, and this is what's quite remarkable, it's independent of the strength of the interaction. So you can take many different crystals, we have different sort of orbitals and different sort of interactions between the electrons. Nevertheless, you get this same universal time that only depends on some fundamental constant of nature. So you have in the strange metal current flowing, but you can't think of the current as being carried by individual electrons or even a quasi-electron. It's really a more collective object that we only dimly understand. And somehow, through that mess flowing around, you also see this remarkable universality. So here's actually some data from a recent paper by the group of Louis Taillefer and Cyril Proust. So these are various compounds, don't worry what they are. And what they have done is computed tau for these compounds. You first of all find that 1 over tau is a linear function of temperature. And this constant alpha, well, it has values pretty close to 1 across many different compounds, which have very different sorts of orbitals and interactions. You'd expect things to vary much more than they do. So somehow, for some reason, when you have this current flow without quasi-particles, it has this time that's controlling how current flows, which is just given by this fundamental constant, h bar divided by temperature. And this is remarkably similar to what you find in black holes. So in black holes, there was a ring down time. You can take many different sorts of black holes with many different characteristics, and you find, again, this similarity. So there seems to be some bizarre similarity between very, very different systems. We know for sure that quantum entanglement is playing a role between them, but it's kind of amazing that they also have this quantitative connection. Okay, so the rest of my talk is to try to give you a flavor of how we are beginning to understand this remarkable similarity. All right. So what is this strange metal? Well, we don't really understand it, as I've said, but we have some idea. And I'm just going to give you one picture that some of us are working with. It's not fully accepted yet. But one of the ideas is that there's down here, there's some kind of critical state with some very special properties. In particular, the properties of these states have entanglement extending to very long distances. And because of that entanglement, you get this universality that there's a typical relaxation time of the current, which is just h bar divided by temperature. So let me just illustrate that by some pictures. Okay, so here's my set of electrons on a square lattice of copper atoms in some configuration. Now let me entangle them. So what we believe happens near this critical point, that the electrons are entangled with each other. For example, there, just like in a hydrogen molecule. So right now, this electron is entangled with that one, because this ellipse represents this particular state, up, down, minus, down, up, that I introduced a while back. And so now these two electrons are entangled, these two are entangled, and so on, but this one is not entangled with that. Okay, well, however, we can fix that. So what happens in this material on its own is that this is not really the complete picture. You can actually, the electrons can exchange partners. So if you look at this particular four set of electrons here, so right now electron 1 is partnered with electron 2 and 3 with 4. Well, they can exchange partners right there. And now all 4 are entangled. So that's really the state. It's both this way and that way, and so on. So it's the same idea of superposing different physical states, but now you're superposing states of more and more and more electrons. And now you can keep going. You can entangle those. And now you can even move an electron that way, and so on. You can entangle them, and so on and so forth. So what's happened in the end is that you've got entanglement which extends over very large distances just on its own. And this is something we believe happens at special points in the phase diagram we could call quantum critical points. And somehow it's the essence of those quantum critical points or phases that we believe leads to this universal h bar over temperature relaxation time, at least in this case. Okay. So that's the summary of what I've just said. The long-range entanglement in the quantum critical state near this critical point leads to, first of all, the absence of any quasi-particles, so you don't have current flowing in lumps, and also just this one time h bar over temperature controlling what goes on. All right. Now, we don't really have a complete theory of this. Much of this is conjecture, but supported by a lot of theoretical work in simpler cases. So we do believe it's true, but the problem is still extremely hard. Just describing this entanglement in some compact set of equations for trillions of electrons is one of the great challenges of what we call quantum many-body theory today. Okay. All right, so now let me try to put the two sides together. I told you about black holes, and there are three properties. Remember what they are? They have a temperature, the entropy is proportional to surface area, and they're controlled by this Planckian time. And then I've told you about strange metals, which have also the same Planckian time, probably due to long-range entanglement of the electrons of the sorts I've illustrated. All right. So here's actually a summary of what I just said. These are the three properties of a black hole. And we'd like to understand these properties from a more fundamental sense. These are, somehow came out of very clever arguments, starting with Hawking and Bekenstein, and many extensions thereof. So nobody doubts they're correct, but it's far from, we have no understanding of what the degrees of freedom are and how do they all lead to this behavior, and what's really the entropy, what is at the microscopic scale responsible for the entropy. Okay, so one of the great ideas that has come out of quantum gravity and string theory, which explains some of this, explains in a little bit in quotes, because we don't quite know if that's the full explanation in our universe. But anyway, it makes a lot of this much more reasonable, is the idea called holography. So here's the statement. So if I look at these properties, black holes have a temperature. Well, strange metals have a temperature. Strange metals or quasi-particle, non-quasi-particle system also have this Planckian time. So maybe black holes are secretly strange metals or something like that. But we run into trouble with this one. In a strange metal, the entropy should be proportional to the volume. It's just an ordinary piece of crystal. It's certainly proportional to the volume. But in a black hole, it's not true. It's proportional to surface area. So how do you make this compatible? Well, what came out of the work of many brilliant people, some of who are cited here below, is that, yes, in some sense, black holes are like strange metal, but the strange metal doesn't live in the volume of the black hole. It lives on the surface. Hence the word holography. You're mapping a three-dimensional black hole to a two-dimensional image, which is this quantum system. And in particular, it has to be a quantum critical many-particle system without quasi-particle excitation. Because only then, if you have a system without quasi-particle excitations, could you get this Planckian time appearing. If you take any other quantum many-particle system, quasi-particles just reappear, no problem. You have to get rid of quasi-particles, and only then will you get this universal time just given by Planck's constant and the Hawking temperature appearing. So what came out of the work in string theory was that you could find explicit examples of this. You could take certain strongly interacting many-body systems and show that from a different point of view, what we call a duality, it actually is a theory of a black hole. All right, so this is something I'm just going to have to ask you to take on faith. This is after many years of learning string theory. You learn one of these amazingly beautiful results, which give you an example of holography. But what I want to do in the remaining 10 minutes is to give you a much simpler example, which does something like this, but for a very simple set of black holes, and for which you can almost see how it's working. But you still need a few equations. So this I'll illustrate by what's called a toy model. So this is an explicit model that you can write down. meaning a set of equations describing electrons. If you look at it one way, it looks like a strange metal. If you look at it the other way, it looks like a black hole. And it also obeys the property of holography. The black hole is in one higher dimension than the strange metal. And so it gives you, explains, if you wish, at least in this simple context, why black holes have these properties and where this universality is coming from. It's all traced into ultra spooky entanglement, really. Okay, so this is sometimes called the SYK model, but I'm going to talk about a very recent variation in collaboration with postdocs and students at Harvard and also Antoine George here at the Flatiron Institute. Okay, so let me just go back to this picture of electrons in YBCO on the square lattice of copper atoms. These electrons are entangled with each other in pairs, and then, as we saw, these pairs can move, they can exchange partners, and so on. But if you remember the old pictures, all of that fancy stuff with things moving around was happening locally, just happening in some region of space where they're just exchanging partners or moving around. And that problem is the one we want to solve, but it's extremely hard. So we proposed that, well, let's make a simplification, because we are so desperate, we just want something that we can understand. So the simplification we're going to make is we're going to allow any particle to move anywhere and allow any pair of particles to exchange with any other particle. So for example, this particle, if it wishes, can move there. And so if it moves there, you get this very long-range bond. That's still entangled with that one as it moved. And there's a number you assign to this process. So this is what we call quantum mechanical amplitude. You assign a certain number to this process. It tells you how likely it is to occur. In particular, the square of that number is the probability that process will occur. And so you assign some number for this type of process. And the key thing that makes this work and makes the problem solvable and tractable is that you just make that number a random number. So for each process, you flip a coin, say, this is the probability that happens. Just pick any random number. And amazingly, once you pick random numbers, the whole thing can be solved. Okay, so for example, this one wants to move there. Okay, why not? And that's with some random. And now these four, now you have this bond. So these four electrons are going to exchange partners. That also happens with some random probability, and so on. So you just pick any. Now I'm picking those four electrons. They exchange partners, and then this one moves there, and so on. So everything that can happen does happen with some random probability. So this is like the anything goes theory of quantum entanglement. And amazingly, this particular model of all possible processes happening with random probability is not fully solvable, but almost completely solvable. You can actually work out what happens. And amazingly, you get exactly what you hoped for. You haven't thrown away the baby with the bathwater by making it so non-local. You still kept the entanglement in an interesting way. And what do you find? Well, this thing turns out, depending on how you look at it, both a strange metal and a black hole. So let me just give you a flavor of how that works. So to describe a strange metal, I really have to have some sense of space, make things move from here to there. And people have done this in various ways. I won't go into any of the details. You take little regions of space where you have this non-local entanglement, and then you allow charges to move around between these regions. And you indeed find that the resistance is proportional to temperature and also associated with this characteristic time of order h bar over temperature. Okay, so that's the easy part. Now, why is this a black hole? Okay, so let me tell you what this system is equivalent to. So I've told you this, I have this region of these electrons here, moving around wherever they wish and entangling with each other with some random amplitude. That turns out to be a description of a particular black hole. And let me tell you what that is. So we start with actually the theory of our universe, which is electromagnetism and Einstein's theory of general relativity. Uh, and the black holes that we have in our universe basically obey those equations and can be described by those equations. But I'm going to do something that's a bit unusual, just because I need to make it map onto the SYK model. I'm going to give the black hole a net charge. So this region of space has more negative than positive charge. Now we know that like charges repel, so this system wants to blow apart, but the gravity keeps it together. And so if you put too much charge, it will blow up, but there's a certain kind of limit before which it doesn't blow up. And you want to put enough charge that it's not too far from that limit. Okay, so you take what's called a charged black hole. And you just solve Einstein's equations and Maxwell's equations for gravity and light near such a black hole. So these black holes have a very special feature, which is why we need them, is that if you come in very close to the horizon of the black hole, you can pretty much ignore this angular direction. Basically, every point on the black hole decouples from all the other points on the horizon. So I won't, you have to really study the equations to see why that happens. I didn't know about it until somebody showed me that this is one of the properties of these black holes. I don't have a particularly intuitive explanation of why that happens, but it does. And so if you're close enough to the horizon of a black hole, you can pretty much ignore all the other points on the surface and think of this as a black hole in one dimension, the radial direction. So effectively, these black holes, by Einstein's equations, are predicted to be essentially one-dimensional black holes at low energy. They live along the radial direction. And of course, there's time that's just determining their quantum entanglement. So you have a theory of gravity with a black hole in one space and one time dimension. So by holography, if you want to now map this onto a quantum system with lots of entanglement, you have to reduce the dimension. You have to go from 1 to 0. Well, that's great, because this system here is practically in 0 dimension because there's no sense of space. It's not as if this point is far from that point because it can jump anywhere it wants. It's really like a point. Every place can go anywhere else. It's like just a little lump with no sense of space. So it is essentially a 0-dimensional system. So so you can then ask, what is the quantum system that describes entanglement along this one direction? Well, that should be a quantum system in 0 dimensions by holography. And it turns out to be exactly this model that I've shown you. So there's actually a very precise and amazing mapping. You could start with Maxwell's equations and Einstein's equations, and then you combine them with Schrödinger's equation in some way. You go to this 2-dimensional space-time along this direction zeta, and you get a set of equations that describe, how gravity interacts, behaves quantum mechanically. So this is coming from the original gravitational description. Secondly, you can start with this model I showed you here with all these entangling electrons and try to write down some equations on the fluctuations of the energy of the electrons, how they evolve in time. And amazingly, when you do that, the energy and the entropy of those electrons obey a set of equations which are exactly the equations you obtain from Einstein's and Maxwell's equation for this 2-dimensional space-time. So that tells you that this low energy limit, the near horizon limit of an ordinary charged black hole, is in fact described. Its entanglement is described or obeys the same equations by this very random model of entanglement that we cooked up in trying to understand strange metals. Okay, so this particular mapping is quite remarkable because both sides are very easy to work with. And many people have worked on ideas related to this, not just to understand superconductors better, and we continue to work on that, but also fundamental questions in the black hole information problem, in particular the question of what happens when you throw something inside a black hole. The black hole state changes in some way, and therefore, the radiation that's coming out of the black hole must change also in some way. But exactly how that happens has been a very difficult thing to understand. And having these simple models is leading to some progress in understanding how that information that you throw into a black hole eventually comes out in the Hawking radiation. Okay, so that's pretty much towards the end of my talk. I thought there'd be more physicists here, and just to prove that I'm a physicist, I had a few equations. So I won't actually just, okay, this is just for a few people in the audience, but you can also entertain yourself in actually seeing these mysterious equations. So what is this mysterious equation that describes both quantum mechanics on the surface of a black hole and also the entanglement of these electrons where anything goes, any electron can entangle with any other electron. All right, so here's what's called the metric of space-time for this higher dimensional black hole. So as you zoom in to the near horizon region of the black hole, you get a metric in one space and one time dimension. This zeta coordinate I showed you here. Yeah, that's the zeta coordinate there. The rest of it is the radial coordinate. You just forget about it. And this is the electric field on the surface of a horizon. So this turns out to be what's called the metric of ADS2. It describes the gravity near the surface of a charged black hole. Okay, so now it turns out that there is some remarkable mapping between what you get out of semi-classical gravity near such a metric and what you get from the SYK model. The entropies have exactly the right temperature dependence. They depend on the charge of the black hole in exactly the same way. And also, furthermore, eventually when you go away from the horizon region, there's a boundary where you go off to, nearly flat space far away. And this boundary also has quantum fluctuations. Amazing, and this is something that Katev and Maldacena showed, that even this boundary fluctuations connect to the subleading equation that describes fluctuations of energy in the SYK model. All right, so these are some of the references that established all these connections. Yeah, I'm sorry. I know I'm losing most of you, but just to show you that I do more than just draw silly pictures. So the precise statement is you take this model with mean interaction U, with the fermion number Q at temperatures smaller than U, or you take a black hole of charge Q and radius RH and temperatures much smaller than RH, and there's a quantum theory that describes both of them. Okay, here it is. It's some kind of described by an action for a phase field and a time reparameterization, and this action can be derived two ways. You can derive it from Einstein's equations and Maxwell's equations, or you can, and quantizing them, or you can start with these electrons doing their entanglement dance where gravity didn't appear at all, and you end up with a theory that looks like gravity because of the long-range entanglement. All right, so that's it. So basically, what I've hopefully gotten across, that quantum entanglement is fun. It's everywhere. It's very hard to control, but sometimes in certain materials and near black holes, it can become quite long range on its own. And amazingly, the long-range entanglement near black holes and also in certain metals and superconductors seem to be connected to each other in some remarkable ways. There's some sort of universality in what happens when quantum entanglement becomes long range. Thank you.